The concepts of subcooling and superheating are probably the two most important principles that a service technician must understand before attempting to systematically troubleshoot air conditioning and refrigeration systems. With the rapid transition to alternative refrigerants and escalating energy costs facing the refrigeration industry today, more attention is being paid to operating costs and system efficiencies. Inattention to system pressures and liquid subcooling can make systems very inefficient. Subcooling is defined as the difference between the measured liquid temperature and the liquid saturation temperature at a given pressure. As soon as all of the saturated vapor in the condenser changes to 100% saturated liquid, subcooling will start to occur if further heat is removed. The heat removed is sensible heat, as the refrigerant is changing temperature. The more heat removed, the lower the temperature of the refrigerant and the greater the liquid subcooling. Liquid subcooling may occur in a system anywhere from the start of the 100% saturated liquid point in the condenser to the metering device. It is important to know why a system must have the proper amount of liquid subcooling, as the amount of liquid subcooling affects system capacity as well as the effectiveness and capacity of expansion-type metering devices. There are two subcooling categories: condenser subcooling and total subcooling. Condenser subcooling is the liquid subcooling present at the point where the refrigerant leaves the condenser. This can be measured by subtracting the actual condenser liquid temperature at that point from the saturation temperature of the refrigerant measured at the condenser outlet. When subcooled, the liquid refrigerant is not generating or losing any vapor pressure, so there is no pressure-temperature relationship, and a pressure-temperature chart cannot be used to obtain the temperature of the refrigerant. The condenser outlet temperature must be measured with either a thermistor or a thermocouple fastened to the condenser outlet. The saturated temperature may be acquired by reading the condenser pressure on the condenser outlet with a gauge, then using a pressure-temperature chart to find the saturated temperature of the refrigerant. If pressure drops exist in the system, the pressure must be measured where the temperature was taken to obtain an accurate liquid subcooling amount. Total subcooling encompasses liquid subcooling from the 100% saturated liquid point in the condenser to the expansion valve or metering device. This means that total subcooling includes condenser subcooling and any subcooling that takes place after the condenser. Liquid can lose heat and subcool in the receiver, filter dryer, and liquid line before it gets to the metering device. However, if there is any refrigerant vapor in the receiver, the subcooled liquid will not subcool further. The vapor will recondense to a liquid in the receiver, and both the liquid and vapor will reach a new saturation temperature. As the vapor recondenses, it rejects heat, which will be absorbed by the subcooled liquid. Subcooling can be lost in this situation if the liquid stays in the receiver too long. Subcooling of liquid rarely occurs when a capillary tube metering device is used because of the severe pressure drop of the liquid as it travels the length of the capillary tube. Due to this reduction in pressure through the capillary tube, the liquid may actually be saturated with flash gas present. Because of the difficulty measuring the temperature at the capillary tube outlet in a service environment, assume that total subcooling ends at the capillary tube entrance. The concept of total subcooling is meaningless without incorporating pressure drops into the equation. Total subcooling can be calculated by subtracting the liquid line temperature at the entrance of the metering device from the saturation temperature at that point. Condenser subcooling ensures that there is a liquid seal at the condenser bottom so the liquid line or receiver is not fed with vapor. This condition prevents any refrigerant vapor or non-condensables, such as air, from leaving the condenser. On systems with no receiver, condenser subcooling can be an indicator of how much refrigerant charge is in a system. Another important reason why condenser subcooling must be present is to prevent liquid line flash gas, or vapor bubbles, from forming in the liquid line. Liquid line flash gas is primarily caused from a pressure drop in the liquid line. Pressure drop in a liquid line can be caused by any restrictive device, including filter dryers, sight glasses, solenoid valves, shutoff valves, or kinked or undersized liquid lines. There are also pressure drops associated with the length of run in refrigerant lines. The longer the run and the more turns and bends associated with the liquid line, the larger the associated pressure drop. There is also more pressure drop with more vertical lift of liquid.